Okay. This is going to be on, I'm still not used to these glasses 100%. They look all right?
Mm-hmm.
Thanks. Thanks, Matt. Are you just,
I'm serious, sir.
you serious? You're not being like a sycophant, are you?
No.
Okay. You know what a sycophant is? Someone who just tries to tell people what they want to hear, to curry favor. Yeah, Dylan, the last thing I would call you was a sycophant. You simply speak your mind. Okay. If she thinks I'm full of crap, she says, Mr. Darcy, you are full of crap. She would say that. Can you see yourself saying that?
Yeah.
Excellent. All right, now, so we're going to talk about Graham's Law, right? What does Graham's Law have to do with? What is it involving? Give me one word that you think of when you talk about Graham's Law.
Ah.
What is it? Okay, she's screaming, excellent. She actually made screaming a single word, excellent. What else do you think of? Gas, I like that. What is it?
Diffusion.
Diffusion. What else? Diffusion, gas.
Effusion?
Effusion, is that what you said? Effusion, excellent. Okay. Graham's Law, how do you spell Graham? G-R... What's a gram? Is that like a scientific term? What is a gram? Where do they get the name Graham's Law from?
It's a name.
It's a name, excellent. Do you know the guy's first name?
Thomas.
Tom. How did you know that? Very good. Thomas. Thomas Graham. Thomas Graham came up with the idea of Graham's Law. It's Graham's Law of the diffusion or effusion of a gas. What is the difference between diffusion and effusion? What is the similarity and what is the difference between those two terms? Yes?
They both happen when changing states.
They both happen when changing states. Not particularly what I'm looking for, but okay, that could happen. Excellent. What else? Something sublimes, it's going to diffuse, right? Yes? Something boils, its gas is going to diffuse or effuse. Good. What else? Well, let's say I have two cylinders, and these cylinders have a partition. Now this partition you can remove. Okay? That partition you can lift up. Yes? This partition is locked into place, but it has a little hole there. Okay? This one I can remove. And as I remove it, what's going to happen to that gas?
It's going to diffuse.
It's going to diffuse. It's going to diffuse, right? It's going to go from there and it's going to fill up the container, correct? If I sprayed perfume up here, anybody got any perfume with them? Okay, it was a little weird, but that's okay. We have no problem with that, actually. Okay, all right. Thank you, sir. Excellent, excellent. Okay. Fahrenheit deodorant by Dior in the red, kind of burnt red can. I like that. It's very exciting. Okay, so tell me when you see this. Tell me when you smell this, okay? And we'll wait when you can smell it, okay? I'm going to skirt it up there. I'm going to squirt it away from you, okay? Okay? You ready? Excellent. One-handed catch. I like that. Very good. Tell me when you smell it. Okay. All right. So that's diffusion. That deodorant, perfume-ish smell is going to diffuse. Did you smell it yet? Anybody smell it back there? No. Okay. So it's going to diffuse. But this is going to get here by just going through a hole. This is called effusion. and this is called diffusion. Yes? Raise your hand when you can smell it.
Oh, I put it on.
Yeah, Enzo smells it. Oh, Ishmael gets it. Daniel got it. It's working its way back.
Also, the further it travels,
You can't have any.
the less.
The more diffuse it gets.
Yeah. So yeah. the-
Good, less concentrated in its right.
It smells like popcorn.
You smell it yet?
Because there's like smell.
Yeah, it smells here, but not
Yeah,
there.
yeah. Okay, so that's what it is. That's diffusion and effusion. And Graham's law does this. Graham's law relates and compares the diffusion of one gas with another. Would anybody like to read to me Graham's law right from the book, and then we'll discuss it. Then we'll try to put it in your own terms. Amanda, would you do that for me, please?
Alright,
I'm going to write on the board, so you got to do it slowly. You got to do it in chunks. Go ahead.
Graham's law states that the rate of diffusion
I want to say. All right, wait a second. This is getting a little sloppy here. All right, she said Graham's, wait a second.
law
Graham's law
states
states,
the rate of diffusion
states
of
the
a
rates of diffusion, the rates of diffusion
of a gas is inversely
of a gas is
proportional
inversely, we know that to be indirect, proportionate,
to the proportional
inversely proportional
to the square root
to, can I just put that down? The square root
of the gas's molar mass.
of the gas's
Molar mass.
molar, the gas's molar mass.
So the heavier the gas, the harder it diffuses.
Yes, yes. Light gases are faster than heavier gases. That's correct, very good. And if you're going to compare them, this is the equation in which you would compare them. Are you ready? Are you ready? Okay. That the velocity of gas A compared to the velocity of gas B is molar mass, just easier to write, okay, of B over A. Okay, now, can I erase what's on the board so far, with the exception of the equation? Are you comfortable with that? Yes? Okay. Now, I also did, you want some extra credit?
Sure.
You sure? I put a rather lengthy, very thorough, very well done, by the way, just saying, video of the scientists who developed the gas laws during like a 150, 200 year period, starting with Boyle, Charles, Gay-Lussac, Avogadro. Okay? Real gases I put in there too, such as Van der Waal, Dalton. I think that's it. I really hit it hard.
Dalton's the one with the cathode ray, right?
Excuse me?
Dalton's the one with the cathode ray, right?
Dalton's the one with the...
Cathode ray.
No.
What
No.
is that?
He worked on atomic theory, though. When we studied the atom early in the year, we looked at Dalton's theory of atomic structure,
Just experience.
his atomic theory. Dalton was pretty... He died. He was a young man. He was a little younger than me when he died, so he lived a full life. You know, none of the gas law scientists really started off as being scientists. They kind of fell into it. You know, societal things kind of, you know. Poor people were never scientists. Rarely was a poor guy. First of all, women weren't scientists back then. I mean, there were, of course, but that was 1800s. That was near the 20th century. I'm talking about like 1600s, 1700s, early 1800s.
Lavoisier.
Lavoisier was a guy.
Yeah, his wife used to help him out.
Yes, very good. Mustafa, very good. Yeah, Lavoisier's wife used to help him out. Exactly. Let's do a problem. Can we do that? Can we do a problem? Okay. So let's do, if you have a book, if you don't have a book, that's fine. Let's do a problem from the back of the book. Let's do problem. We're going to do problem 87. Shall I write it on the board? A certain gas effuses. A certain gas effuses. Does it say diffuses or effuses? Effuses 4 times faster than oxygen. Right? What's that noise? Was that this? Was that you? Okay, that's okay. What is the molar mass of the gas? What is the molar mass? U, I put U for unknown. What is the molar mass of the unknown gas? Okay? Now, if anybody really cares, see Mr. Nair and he'll set up some counseling for you. Okay, sorry, my apologies. All right, so I know, chemistry is full of these kind of word problems that are not nearly as exciting as Star Wars Episode 7 coming out soon, hopefully in the next few years, hopefully before I die. Yes?
You can smell it. No.
You can smell it. Okay. Finally got back. You know, molecules travel very quickly. I mean, they're very fast. How come it took so long to get back just that little bit? How come it took so long?
Had to fill the whole room.
What is it?
Because it had to fill the whole room.
No, not this. It's right there. She's right there.
Yeah, but you sprayed it like that way.
Yeah, but no, I sprayed up here, but why did it take so long to get there?
Because it gets thinner and thinner, so it's
It
harder for
loses
control.
its smell as it's set down.
Yeah, but no. Yes, yes. I will say yes to all of those, but that's not really specific enough. Why does it? What is it? She has a bad sense of smell. I like this, establishing all the extraneous variables. What else? So why does it take so long to get to her?
There's no.
We did a little bit of a demo. I sprayed some perfume.
I surmised.
Yes, and she's just getting the smell of it.
If,
Yeah.
what factor were you like? If there was like air like blowing at it, would it go like?
Well, what is the? Are you breathing right now, or are you like a vampire? You don't have to breathe.
I'm breathing.
You are breathing. Okay, and what do you breathe? Air. What's the average atomic weight of air? Average. The average molecular weight of air. Just average. Just shoot me a number. Ish.
So like
I was gonna say
nitrogen, oxygen.
Yeah, it's like 80% nitrogen, 20% oxygen.
Say 20?
Well, oxygen's what's the molar mass of oxygen?
6?
No, 6. What planet are you from? On my planet,
16.
no, of oxygen gas.
Oh.
32. What's the molar mass of nitrogen? 28. What do people use as the average? Just for your, this is actually, they use this in industry.
30.
29. They actually use 29. So we don't know what that gas was made out of, but it's probably pretty light, right? But what's in the way? What's between the gas that I sprayed out of the can and Fabiana?
More air.
Air. And is air moving?
No.
Yes.
Air's not moving?
Well, it is
In
moving.
here,
but not
yeah, but
It's moving really fast.
The opposite way.
Right. What's all right, tell me one of the most important aspects of ideal gases. Now, we can treat air ideally because it's between STP and 100 degrees. So it's like, it could be treated as an ideal gas, couldn't it be? Air, right, in here? Yeah. So give me one of the major aspects of an ideal gas. One of the major things. What do molecules do? They move, and what do they do when they move?
Bounce.
They what?
They bounce.
They bounce. We don't use bounce in chemistry, okay? We don't like the word bounce, okay? It's too friendly of a word. We call it collisions. Mr. Nair knows all about possible collisions. Okay, ask Mr. Nair his collision story. Okay? So what kind of collision do gases have with each other? Starts with an E and it's not elephant. Elastic collisions, right? Where no energy is lost, energy is transferred, yes? So all of these molecules, I'll put you out of your misery, shall I? The molecules between the gas and you, Fabiana, the air, is bumping the gas that's diffusing. And when gas collides, it does what? It doesn't stop. It goes in different directions. It could bounce back. And it finally will get to you. Can you imagine trying to make your way down through Times Square in New York City at 11:58 p.m. on December 31st of 1999? Could you? Which is not the end of the millennium, although some people thought it was. But could you? It would be amazing, wouldn't it?
What?
It's not the end of the millennium.
How's that not the end?
Because the end of the millennium is the end of the 10th year of the decade. The 1000th year, see?
The 10th.
Count to 10.
1, 2, 3, 4, 5, 6, 7, 8.
Okay, and what'd you start at?
1.
Didn't you start at 0? You didn't? Yeah, okay, so can you make your way down the street through Times Square? I mean, it would be hard, right?
It's hard.
Yeah, well, that's what the gas that I sprayed. There's a lot of stuff between you. So when you're talking about the effusion of gas, you have to talk about the effusion of just that gas. I wasn't losing my mind and going off on a tangent. When you're talking about Graham's law, you're talking about essentially the diffusion of a gas, or comparing two gases, not 20 gases that make up a cylinder, but a vacuum or just that gas. Clear? So I have a gas, a certain gas diffuses and it's unknown, and it's going to diffuse 4 times faster than oxygen. So what would the ratio, let's say that A, let's change this. A is unknown, B is oxygen. Then B over here would be oxygen, and then A is unknown. Is that correct? Is that correct? Okay, now plug it in. What would this ratio be if it says on the board that the unknown gas has a velocity 4 times that of oxygen? First of all, what do you know about the answer? Is it going to have a molar mass less than oxygen or greater than oxygen? Greater than oxygen. Excellent. Is that true? Greater than oxygen?
Yeah, because it diffuses faster than oxygen.
No.
Okay. All right. So the unknown gas will be heavier than oxygen. Is that what you think? Excellent. Okay, good. Excellent. Now, so let's put in some values. Let's put in some values. And we're going to say 4 equals what? 4 equal, hold your question, I know what you want to say. 4 equals 32 over the unknown, correct? All right. So it'll be 32 over MMU, correct?
So
Square both sides, what do you get?
it's 16 equals 32 over MMU.
16 equals 32 over MMU, correct? Now, solve for MMU if you are
16.
comfortable with proportional relationships. You just flip-flop MMU and 16. MMU, Mr. Videographer, am I on?
Yes.
MMU equals
Two.
32 over 16. So what's the molar mass of the unknown gas?
2.
2. And 2, of course, is greater than 32, isn't it?
Yes.
No.
Well, in this.
Didn't-
2 is not greater than
32.
2.
Because if the gas infuses faster, it's lighter. So
I
it's
was thinking of it in a different.
Now, let me ask you again. Okay, let me ask you again. The unknown gas is 4 times faster than oxygen. Now, based on what we discussed about 10 minutes ago before we started filming, would the gas be heavier or lighter than oxygen?
Lighter.
Mustafa, are you here today? Now, when you packed your bags this morning, did you pack both hemispheres of your brain? Some people forget the other half. I understand it's a common mistake.
Is oxygen 4 times faster than the gas? Or is
Now, listen to the problem. Listen to the problem. A certain gas effuses 4 times greater than oxygen.
That certain gas is 4 times lighter than oxygen.
4 times lighter than oxygen?
Proportionally.
Amanda, what did you read? Read that. Remember you read Graham's Law, Amanda?
Yeah.
All right. Look, can I erase some of this stuff on the board?
Sure.
Is that okay? Okay. So let's erase some of the stuff off the board. Okay. Okay. All right, so, Amanda, what did we discuss? We discussed that the molar mass of the unknown equals 2 grams. And what's that gas probably?
It's probably
Hydrogen.
Hydrogen, very good. Probably hydrogen, excellent. And what we said was that the unknown gas, the velocity of the unknown gas, is 4 times greater. It's 4 times greater than the velocity of oxygen, correct? Yes, didn't we say that?
Yep.
Now, Amanda, read to me what you read earlier.
Graham's law states
Graham's law states, I love the South African accent, carry on,
that the rate of effusion
the rates of effusion
of a gas
of a gas
is inversely proportional
is inversely proportional to
the square root of the gas molar mass.
the square root of the gas's molar mass, or vice versa. Couldn't you say that?
Yes.
Right? You get it? You understand? Is that consistent with that rule?
Yes.
Absolutely. You get it? Graham's law. Sir?
I have a question.
Yes.
I did the math in my head, so forgive me if I did my arithmetic
Understood.
wrong. But it seems like lighter gases diffuse, I think diffuse is close to a fusion to spread out, faster than heavier gas.
That's correct.
Okay.
That's what we, see,
That's what we-
the students said early on, you can go that way.
Heavier
Don't
gas,
hit
because they
the,
were doing F equals ma probably, right? They were thinking force equals mass times acceleration.
I'm not sure, I don't know. That's giving them a lot of credit, Mr. Nair. I'm not sure what they were
But if
thinking.
you do F equals ma and you have a bigger mass, then you're gonna have a smaller acceleration.
Correct.
For less motion.
Correct.
Forgot.
Correct. Because what's the relationship between M and A? It's a product, so what's the relationship between the factors of a product? It's indirect, not direct. M is indirectly related to A, right? Because it's a product, right? Okay, are we done? Are we done that problem? We'll revisit Graham's law. We'll revisit it. But you all right? We're off.
My brain is full, so now I go.